logic is...
Does my hair... Oh my god! That's... What?
No, he's here. He's right there.
He tried calling me at 10:30 last night asking about the physics homework, and I did none of it. End my life.
His logic was that nobody would guess it as a password if it was too obvious. At which point, when you think about it, the reason your password should be hard to get is not because people are going to try and get it.
Because robots though.
Exactly. And the robot will get that the first try every time.
Oh my gosh.
So here you go.
Anyway.
No, I don't want a new folder. I just want
Let's see what the homework was. The twin paradox.
Oh god, not that again. That's how you spell homework.
The answer, by the way, to 2 is greater than T needs to be 3.
Ow. Hello. I want to die.
Okay, so here we go. That's cool. All right, number 1. If the student arriving at the origin of the teacher's coordinate, the teacher marking him's coordinate hint, did I say hint? Did I specify? Yeah, right? Him. The teacher marking him party would be at negative 0.7 milliseconds, 10 meters, 0, 0. Or you could reverse it, which just changes the sign of the time coordinate, right? The teacher marking him is the origin, and the student would be at 0.7 milliseconds, right? Just make sure that the teacher has to be before the student. Okay. Number 2 is, in exact terms, would be 0.00007 c squared seconds per meter, or, if you prefer kind of more sensible units, about 1.3 times 10 to the 21st meters per second. And number 3, the answer is C. Okay, number 4 is after 1.005 years. Number 5 is 19.1 years old, 19.11 if you like. Number 6 is also 19.11 years old, even after I fix the problem and change it so that it's not the same. Repeated, it is the same answer repeated. Number 7 is D. Number 8 is, again, after 1.005 years. Number 9 is 19.11 years old. Number 10 is 19.22 years old. Number 11 is D. And number 12, although that's a challenge, so we're working on that. The answer is 7.9 seconds. I think that's exact, but I'm not actually sure. Might not. Okay. Questions on the homework? Yes. Number 10. Depends on how old you receive this something order, right? Okay, so in this one, the random number generator gave us a pretty slow speed, so the differences aren't that great. We have 0.1c is our velocity, so gamma or 0.1c is 10 over root 99, so 10 over 3 root 11. Right? Is that right? Okay. That's just for reference. You're going to need gamma, right? Okay, so what we have is, who's on the planet again? Remus is on the planet. References to?
The founding of Rome.
Good, the founders of Rome. The twins, Remus and Romulus, raised by wolves, all that stuff. For shame. All right, good. So,
I always said Romulus and Remus.
That's not like nerd culture, though. That is just like that's sort of like actual culture. Rome, the most important empire ever to exist, right? Except for America, because we think we're the best things ever. But the Romulus goes out like this. The big difference between this problem and the twin paradox that I showed you before is that in this problem, because Romulus never turns around. So now Romulus never turns around. You're like, what now? Right? But the problem is when Romulus doesn't turn around, there's no longer a paradox. And the reason is because how do you tell what age they are? So the set of problems gives you two different ways that you can tell their age. One of them is they'll each tell each other what their age is via some sort of signal, right? But by the time those signals reach each other, they'll each get the signal after they send their own, right? And then the other one is that this one, which is Remus sends the signal first, right? Yeah. Okay, Remus sends the signal to Romulus, Romulus receives it and sends his own signal back, right? So, so here's how it works. When 1 year has passed for Remus, right? Now he sends his light signal out, which of course goes at c, the speed of light. In that time, how far has Romulus gone? 0.1 light year, right? Because he's been 1 year, he goes 0.1 c. So Romulus is 0.1 light year away. Okay. He is still moving though at 0.1 c, right? So how long will it take the light beam to catch up to him? We'll take a little like, hey, wait, actually it's not that clear. Okay. So you're like, well, here's basically what it is. In the meantime, this guy's still moving, right? So he's going to go a certain further distance, right? Okay. And so let's say there's an overall time that we'll calculate, right? That's what we want to know. So this would have to be 0.1 c times the time that the extra time it travels, right? This is all the same references. This is all in Remus's reference frame. Okay? In the meantime, the light has to go the whole way, right? This whole way is going to be the speed of light times that same time, right? Because it's that same time, because after that amount of time, that's when the light catches up to him. Okay? From using this picture, now you can, this by the way is an algebra solving technique. Like you should have learned at some point in algebra, but whatever. So you can do CT equals 0.1 light year plus 0.1 CT. You see? The total distance, which is how far the light goes, has to equal how far he was plus how far he goes in the after the light's fired. So you can do it that way. If you do it that way, you get 0.9 CT equals 0.1 c light years. The c's cancel out, and the minus, you multiply by 10, and you get 1/9 of a year, which is 0.11 years. And therefore he will receive it in Remus's reference frame. He will receive it after 0.11 years. Okay. Then what does he have to do? He waits until Romulus waits until he receives the signal, then says, "Okay, I got your signal. Here's all I am," right? And he sends that back to Remus. Okay. How long will that take to get back? This is an easy one. Another 1/9 year, because he sends it immediately, presumably, right? So it has the exact same distance to go back in Remus's frame. So therefore, Remus's frame is the straightforward one. It comes right back, takes 2 nights a year total, and everything's fine. The question I didn't ask, that I should have, was how old will Romulus say he is when he sends it back? To find that out, you'd have to do a time dilation to figure out what's going on in Romulus's reference frame when he receives this. But I forgot to ask that. So. Okay? Yes?
Okay. Second question, nice segue from the end of that, is how do you know when to do time dilation and when to do Lorentz? And the same for liquid.
What a great question. Okay, so here's how it works. The main thing is, you say, well, I'll just use Lorentz transformations for everything, right? Well, first of all, if you feel comfortable with Lorentz transformations, then that's not so bad, right? You have to set up an origin and stuff, and for some people it's a little bit laborious. This is not like this is just what people prefer, right? For some people it's like, oh, right, the origin, and that's not the way they like to think about things. Some people, that's totally the way they like to think about things. Lorentz transformations are no big deal. There's, if you do Lorentz transformations for a time dilation problem, everything should work out fine. There's no real danger. The danger is for questions of length contraction. Okay? Length contraction has some subtle trickery with Lorentz transformations. If you try and do it that way, that if you try and do it yourself, you are likely to mess it up. So I would say this. If it's a question about how long something is, the answer is usually done with just length contraction. Or at least try to do it with length contraction. Now, when you have a question of time, then it's just a question of how quickly can you do it. Why do you use Lorentz transformation? Why would you not just use regular time dilation, which is faster? if neither reference frame has the proper time, right? So you can look at these. What are we measuring the time between? Well, we're first measuring the time between, for example, 1 year in Venus's time, right? So, him turning 17, or 16, him turning 16, him turning 17, right? But those would happen in the same location in his frame. We have a frame with the proper time. Usually what you have for Lorentz transformation problems is things happening in different places and different times in a given reference frame. Okay, because then you're stuck. You don't have a proper time or a proper length because the locations are different and the times are different. Then you should use Lorentz transformations. Micah.
Didn't we previously do a problem that we didn't have proper time, but we were able to work around that and still use length contraction?
Length contraction, you don't need proper time for length contraction.
Or not proper time, proper length.
There was that one, the Ford and Arthur problem from the quiz, where neither Ford nor Arthur had the proper time, but you were given the proper length. No, you weren't given the proper length. You could do it in terms of proper length, yes. And that's the way you want to do it, because as the length, when asking about the length of things, like I said, you generally want to use length contraction and not Lorentz transformation. What Lorentz transformations are really good for, that are very hard to do any other way, is questions involving simultaneity, involving things happening in different times or in different orders in different reference frames, right? Or simultaneous in one and not in the other. Those are very difficult to solve any other way. So that's where Lorentz transformations come in. Yes, ma'am.
Can you just give like an example of a question where like there's two different events and they happen?
Sure. There's a train going along, and then on one end of the train, a bomb explodes. And then 2 seconds later, in the train's reference frame, on the other end of the train, a bomb explodes. Right? A common one that they do is the bomb explodes and leaves scorch marks on the ground. Right? So what's the distance between those scorch marks and the Earth's reference frame? Okay. That one, you see, it's not a question of what's the length of the train in the Earth's reference frame, which is a simple length contraction. But this is about these events that happen at different times. Right? Because they happen at different times, they're given no proper time information. They have different times at different locations. They have no proper time information, right? You cannot do a length contraction because it's not asking about the length of an object. It is asking about how far apart are these things. So really what you want are, what are the x-coordinates of those explosions in the Earth's reference frame? And so that's a perfect one to use Lorentz transformations. My pleasure. Are there other questions I can answer as well? Yes, Matt.
For the first multiple choice one, was there like a difference between saying B or C?
Yes.
Okay.
I'm glad you asked that. Okay. It is true that the student cannot move faster than the speed of light, but I actually haven't told you why yet. Okay. People often jump to sloppy conclusions on this one. Actually, it is physically, let's see, the theory of relativity allows things to go faster than light, actually. But they have to have some unusual properties that do not match the properties of things we have. In fact, the issue in relativity is an asymptote. You can go faster than light or slower than light, you just can't cross the speed of light boundary, is how it works. And we'll explain that, and you'll see how that works. But the point is, there's nothing about this that is about the student's speed. In fact, if you think about it, the student's speed is not the question, right? It's not the student's speed. It's the question, the student is not making a claim about his speed. What is the student making a claim about? Right, he claims that there is some reference frame where he gets in on time, right? That's the claim. So you solve for the relative velocity of that reference frame, which is not the student's speed. It's the speed of some reference frame relative to the classroom reference frame. And so you solve that and you find out a ridiculous velocity. Why is it a problem to get a ridiculous velocity? A reference frame, remember, is not a thing, right? What is it? It's a mathematical object, right? It's like a mathematical concept, right? It's not you don't see reference frames going on. You assign them mathematically. They're coordinate systems, right? So it's no big deal to have a reference frame moving really fast. That is not a problem at all. You don't have to put engines on it. There's no issues involving with it. You don't have to worry about its health, right? But so tell me then, what is the problem with the reference frame going faster than light? A lot faster in this case, right? What is the problem with it? You don't have to assign it for an object to a reference frame. All you do is velocity.
I figured the answer was just like there. No. And we'll have to. Well, yeah.
So,
Okay.
okay, you're getting better. Gamma would be what? Imaginary. As a result of gamma being imaginary, then what? Then all space and time coordinates in that reference frame would be imaginary, meaning what's imaginary mean in physics?
Doesn't exist.
Doesn't exist. It's meaningless, right? So that reference frame is not a physically meaningful reference frame because it gives no physically meaningful answers, right? Therefore, the problem is that it's the reference frame that's going too fast, not the student. Okay? There is a problem with the student going too fast, but it's actually not this one. This is the problem with a reference frame going too fast. Okay, do you understand what I'm saying here? Does that make sense? Say it again? No, that's what we just showed, right? Because you can claim that there's a reference frame, but you're wrong. But that was 0.7 milliseconds. You don't usually come in that close to the bell, to the cutoff. Usually, most teachers are kind of lenient on 0.7 milliseconds. So that's, but that's the key is that the only reference frame which would happen is a non-physical reference frame, a physically meaningless reference frame, which I do not accept as an excuse then. Do you have a question? Yeah. Okay. It'd have to be, you can calculate what it would have to be. In fact, you can just take your work for that problem, set the answer to 0.99c, and then work backwards to figure out what the time would have to be. And you'll discover it's a lot less than 0.3 milliseconds. Much smaller number. It happens whenever you run into the speed of light. Your numbers have to get really big or really small. In this case, it would have to be a lot less than it'd have to be, I can't remember what it came out to, picoseconds, I think, nanoseconds, something like that. Very small. Good. Other questions?
I'm just confused about in senior was talking about
which senior was it? It's okay, right?
Anyway, senior talking about he said that there should be from given any two events with those time, there should be a range to which they are something.
That's incorrect. Okay. Yes, that's incorrect. Some events can be, so the statement that is true is if two events are simultaneous in one reference frame, they are not simultaneous in any other reference frame. However, some events, like the student here, are not simultaneous in any physical reference frame. That's very important to realize. Otherwise, so there's no reference frame in which your birth and your death are simultaneous. Isn't that good to know? Yeah.
Question about number 2, but I think you said the unit.
Units are a little messy. You have to keep track of them carefully. Okay, that's basically the rule. You have to keep track of them carefully. You should end up with an answer in terms of C for a question that's not asking for something in terms of C. You know what I mean? It's not asking for. Number 2 is asking for the velocity, but you end up with. You get an answer in terms of C squared. The velocity you want, it's a velocity, C squared is not a velocity. To get it right, technically, if you follow the units through, you should get something in C squared times seconds over meters. That will give you the total unit. No one uses that unit because it's stupid. So probably what most people did was just numerically plug in for C squared and get an answer in meters per second, which is, I think a better way to go. Okay. Yes?
Can you go over how it's per meter?
In this problem, you're basically looking at this transformation, right? And we're solving for b. And we're letting that be 0. Right? That's how we did it. It's very important that we let it be 0 because then the gamma factor we can ignore, because gamma is never 0, so you don't have to worry about it. So we can cancel it out, and therefore you get t equals b over c squared x, or b equals t c squared over x. Right, so this is doing it all algebraically. Then if you put in the numbers here, you'll get, then you get t was what, 0.7 milliseconds, right? So I say 0.7 times 10 to the negative third seconds. That's just to keep it in the more standard units. Divided by x is, what's the distance between them?
10 meters.
10 meters, okay. 10 meters. And here's c squared. right? So now you can see the units, c squared times seconds over meters, right? Which is a weird unit, so you plug in for this in terms of meters per second, and one of those will cancel out. One of the factors of meters per second here will cancel out the seconds over meters here, and you'll be left with one factor of meters over seconds. The fact is, you don't need to focus on this too much. In fact, you'll see as we go on, we'll do less and less with units. So I would not worry overly about that, but that's where it comes from. Yeah.
I have a question about the Shelby problem. I got an answer, but what I didn't use the time. I didn't use the speed of the person.
Wow, it's almost as if I threw in that number as a red herring to try and distract you. So anyway, Dr. Cobb would never do that. So, real life doesn't work that way. They don't tell you which numbers are important. You have to figure it out yourself. So anyway, now you know. Lesson learned. Okay, any other questions on the homework? Very good. Let us move on. I think we'll go ahead and plan for a quiz on Thursday, which I know is fast. But like it's a good kind of hurt, you know? No, I mean, it's just like there's nothing else to say at a certain point. Otherwise, we go in class and we do worksheets or something. We do worksheets at home, you know? So, yes.
Okay, if we're going to, do our next semester after that class, are we going to, finish the semester with, a month after?
No, it's not going to happen because you see, before we are going to have another test. That was actually a little longer because the material takes longer to cover, so it'll be a little bit longer there. But we will have the next test when we finish the next round of quiz, when we finish the next round of material, and then we will be ready to launch into our project. We will have a break to cover some of the project, which is related. So it won't be. I'm hoping it will be enforced material, and then we'll have an exam. We'll do more project work, and it will slow the pace down considerably once we have project work done.
So there's going to be a point where we're doing the project and not doing
right. Yes. When you're doing project stuff, I do not cover new material. Right? Try not to. Okay. Good. Ready? Okay, let's answer this question that people have been asking. Several people have already asked me. Probably more of you have thought about it, which is, if I am on a train and you are here, and the train is moving at 20 miles per hour, and I'm holding a baseball and I throw the baseball relative to myself with my awesome pitching arm at 50 miles per hour, which is not a particularly good pitch and still beyond what I can handle, then you watching here in awe will see the baseball moving with what speed? 70 miles per hour.
Nice pitch.
Thank you. I need a train to do it. So this is a simple example of how velocity is trained. We did this on the first day, if I recall, right? Straightforward. Good. Now, if I have a train, and the train is going, say, 0.7c, and I am standing here, and I, with my even better pitching arm, throw the ball at 0.5c relative to myself, then you standing here watching in awe, and this would be some kind of awe, will see the baseball move.
No. Less than C?
Would it be going 1.2c?
No.
Something, right? Okay, good. So let's actually deal with this question because let's face it, velocities come up all the time. So we're going to need to deal with velocities, right? The fact is, our simple law for transforming velocities between reference frames obviously does not work. That means we actually have to think about what if we know the velocity in one reference frame, how do we figure out the velocity in another reference frame? And figure out how the Lorentz transformations will tell us how things actually work. So let's take a look. So here's the problem. We have two reference frames, right? As always, we have one of them moving in the positive x direction relative to the other one at velocity v. We always set things up like that. That's just convention. Okay. Now, in this reference frame, there is some object then it's moving with the velocity. Remember what we use for velocity because v is taken? U, that's right. Good memory. We use u just to be precise, I'll use u sub x, going in the x direction. Okay? So, this, in this reference frame, you will see the same object moving, but it will have in general different velocity primes of x. Okay? And so, this is the problem we're trying to solve, right? Okay. To do this problem, we have to remember what is u of x exactly, u sub x exactly. What is velocity? What is velocity? It's over time, right? So mathematically, how do I write distance? You know, no. Come on, guys. Remember SI physics? With what? Delta x, thank you. Displacement, remember? Delta x, and there's a reason we use delta x. Why? How do you really measure distance? You measure the position coordinate here, the position coordinate there, and take the difference between them, right? That's really what you're looking at. Okay, we call it displacement sometimes. Displacement actually is the better word in this case, it's a vector, right? Remember all that? Okay, so it's delta x divided by the time. How should I indicate the time? Should technically put delta t, because while in SI physics we always kept one of the points at 0, really when you're measuring time, as we know, you're always measuring between two events, right? So this really should be delta x over delta time. Okay, good. And u prime sub x should be then, good, delta x prime over delta t prime. Right? Okay, good. Now, those of you who know some calculus know that this is actually dx dt, which is fine. Turns out this all works. The reason this all works is because Lorentz transformations are linear, which they need to be, and so the Lorentz transformations can be written like this. The exact same thing with deltas on it. Okay? That's because those of you who know calculus and say it's true, you can't always do this, but the Lorentz transformations are linear, and therefore you can. Which means, I'm just rewriting the Lorentz transformations with a bunch of primals. Right? I haven't changed anything. I'm just saying it also works for small intervals in delta in x and t, which makes sense, right? I mean, there's no absolute origin anyway, so of course this should still work. Okay, good. So, given that, all I have to do now is substitute this into here, and I'll have my answer. So let's do that. Delta x is delta times gamma times delta x minus b delta t over delta t is gamma times delta t minus b over c squared delta x. Okay. Before we simplify this, let's talk about what's going on here. It says that the velocities that you measure will change. Why will velocities change? Two reasons. What are they? One's on the top and one's on the bottom. What's the reason why the numerator will change? Yeah, what's that? What do we call that? Lane contraction, right? Lane contraction means your measured distances will be different. And on the denominator, time dilation says the times you measure will be different. And they're not different the same way, right? And that means your velocity, therefore, will be different, right? And so you should not be surprised that this is going to give you a different answer. Let's see what comes out. The gammas cancel. Yay. Never like them anyway. It's square roots. That's square roots. Okay. Now you just have this part left over. Let's simplify it. This sort of thing becomes more natural as you practice, but we'll simplify it by multiplying the top and bottom by 1 over delta t. Remember, you can multiply the top and bottom of a fraction by anything as long as it's the same, right? Because that's multiplied by 1 over 1. But we'll multiply by 1 over delta t. The reason is then you get this first term becomes delta x over delta t minus, and here delta t is canceling, you get b. And in the bottom, delta t is canceling, you get 1 minus b over c squared, and then this becomes delta x over delta t. And that's important because what's delta x over delta t? U sub x. Look at that. So I can take that and substitute it back in, making a much simpler expression and a very important one. this, wait, this is important. I shall box it in another color. This is how you know it's important. So this expression is, what am I talking about? Okay, yes. This expression is the actual way you calculate velocities in other reference frames. Okay? You don't just add and subtract things. You instead, you have to do this, which is a bit more complicated than adding and subtracting, but at least there's no square roots. Right? By the way, another good reason to do all your velocities in fractions, because everything is all big fractions and fractions. Much easier to work with if you just have everything in fractions. Okay, so let's apply this back to this problem. Now, here in this problem, it's okay, happens to everyone. Except me, by the way, it's never happened. All right, so in this one, which one would be the use of x and which one would be the v in this problem? But use of x. Good. Use of x is always, it's just our convention, right? Use of x is the velocity of the object, not of a frame, but of an object, right? So use of x would be 50 miles an hour. Don't do that one. Let's do this one. Use of x would be 0.5c. There we go. Okay. Now you have to be careful. Use of x is known in which reference frame? The train's reference frame. Remember that I said I threw it that hard, like relative to me? So that's in the train's reference frame. Right? The thing I want to know is use of prime x, which is in which reference frame? The Earth's reference frame. Right? So v is the velocity of what? Of the Earth relative to the train. Right? Remember that is always the velocity of the frame that you want to know. So v is the velocity of the Earth. What's the velocity of the Earth relative to the train? Negative 0.7c. Okay? That minus sign, this thing, figuring out the sign of v is the most important part. Okay. Once we have that, now we can use our equation and solve. U prime of x is use of x. So use of x is here. Let me rewrite the problem, the equation, so you can see it. Okay. Use of x is 0.5c. All right, 1/2 c minus the v is negative 7/10 c all over 1 minus 1/2 c times 7/10 c all over c squared. So I'm just substituting directly into the equation we just wrote with use of x equals 1/2 c and v equals negative 7/10 c. Yeah. It is. Thank you. Wow. Okay. Yes. You win today. If I were Dr. Skinner, I would give you a high five or say you still might be eating hard or something like that. Okay, yes, it definitely needs to be negative 7 at the bottom, so that would give me the wrong answer, and it would be that. Okay, so what happens? So here we go. On the top, we have 1/2 c plus 7/10 c. I'll simplify that in a moment. On the bottom we have, well, at the very least, there's 2 factors of c on the top and a c squared on the bottom. So all those c's will cancel. That usually happens. We still have a minus sign there, so it becomes plus, right? And then it becomes plus 1/2 times 7/10. The c's having canceled. Okay? I'll leave the numerator alone for the moment and fix up the denominator first. This is 1 plus 7 over 20. Remembering that 1 plus 7 over 20 is 1, it can be written as what? 20 over 20, right? This is 20 over 20 plus 7 over 20, which gives you 27 over 20. Okay? I do it this way because I want to multiply this through before I try to add the fractions on top, but really you can do it however you want. I'll go ahead and also add the fractions on top. It might be more simple. 1/2 can also be written as 5/10, right? Or yes, also 0.5, but you can also write it as 5/10, which makes it easy. You can also add these as decimals pretty easily, right? So this gives me in the numerator 12/10c. Note that your numerator is the same thing we had before that was problematic, but that's the numerator, there's also a denominator. Okay? Now we divide. Divide carefully, invert and multiply, right? So 12 will always reduce right away your fractions. So 12/10 is the same as 6/5c. Divided by 27/20 means times 20/27. Invert and multiply, right? Like seriously, this is an easy step to mess up. Please watch, please take carefully, don't try to show off. And then here, the 5 and the 20 cancel. That's nice. The 6 and the 27 cancel somewhat. That's nice. Always cross cancel first, by the way, right? And then you end up with 6/9c. 8/9. Wow. 8/9c. Thank you. Maybe that doesn't seem right. You end up with 8/9c. And what do you notice about 8/9c? It's less than c. And so you have the proper velocity transformation law preserves the limit of c. Okay.
If we ran through this with non-160, it would still work.
It would. You see it really quickly. Say we use 50 and 70 miles an hour. You have those two. You get that's still negative. B is still negative for the same reason, right? So you get 50 plus 70, 120.
Yeah.
Or what do I have over there? Yeah, 50 plus 20. I did 20 over there for some reason. Okay. 50 plus 20, so 70, right? And on the bottom you have over 1 minus 50 times 20 over c squared, right? So 50 times 20 is 1,000, and c squared is 9 times 10 to the 16, right? And you divide those, you get approximately 0, and 1 minus approximately 0 is approximately 1, and you get a regular answer over basically 1, right? So this denominator is always so close to 1 until you get to relative 6 weeks. Good question.
Right, so technically, the speed in the first problem is the time is a bit less than 70.
True. Technically, the 70% is not quite accurate. And if that bothers you, something is wrong with you. All right. Because the amount by which it is less is, we're talking about, something in the order of 10 to the 16, 10 to the negative 16, which is small. Okay, good. So here's something important. Okay, the way I did this one is the way that matches the way we do Lorentz transformations. If you like that, good, do that. However, I will give you an alternate way to look at it that gives you the exact same answer. This is the way I do it, because I find it slightly faster, but it's not about speed. This is not a race. Physicists are a race, but physics is not a race. It's not true either, obviously. But physics, I mean, it is. This is sort of the master race. So anyway, this way of doing it is totally fine, and if you like this, keep it, right? But if you think of it a different way, here's how it works. Here's the way I think of it. Whenever you have velocity problems, even in regular classical physics, right? There's really only two things you could do. You always have two velocities, right? And you always do one of two things with that. You either add them or subtract them, right? So if you have some velocity 1 and a velocity 2, and I don't know, the problems can get a little confusing sometimes, you have to think through them, right? But you always have some velocity 1 and velocity 2, right? The speed is classically, the speed is either v1 plus v2 or v1 minus v2. I put absolute value signs so it's the speed. I don't know which one's better. Okay? But you always either add or subtract. That always happens, right? Then you have to think, okay, which way is it pointing? Which is usually pretty easy. This you can usually do intuitively. You can just think to yourself, should it be going faster or should it be going slower? Right? Like with the ball here, Should I see the ball going faster or slower? I should see it going faster. The train's like boosting it, right? So plus, right? If I threw the ball the other way, I'd be like, oh, the train's kind of, it's like fighting against it, so it should be going slower, and I use minus. Okay, so this is something that you can do with intuition. Okay, it doesn't tell you direction, so you'll have to dig the direction yourself, right? Figuring out whether it's positive or negative is up to you. Okay, so relativistically, the speed is either v1 plus v2 over 1 plus v1 v2 over c squared, or v1 minus v2 over 1 minus v1 v2 over c squared. Okay, in other words, you can do, and they line up perfectly. So whenever you would want to just add them, you still just add them, but put this in the denominator with a plus sign. Whenever you would want to just subtract them, still just subtract them, but put in the denominator, this in the denominator with a minus sign. Okay? And you'll get your answer. So the thing is, this one lets you follow your intuition, right? If you're like, oh, it has to be something faster, I better be adding these velocities, well then you add them, but put this denominator in the bottom. Okay? Now, I find this easier, because I think it's faster. Some people find this more confusing. If you found that confusing, then don't use it and use the other one, right? Right, so the other way is just you set up your coordinate systems, identify use of x, identify v, be careful of your signs, then just plug it straight into the equation and you're done. And we'll give you the sign of your answer too. This one is an intuitive approach. Should it be faster or slower? Am I adding or subtracting? Then I do this calculation and I'm done. If the intuition works for you, then you should do it. If you don't like that, then don't do it. Fair enough? Okay, just giving you alternate approaches to solve the same problem. You'll get the same answer. If you do either one can be done right, you get the same answer. Okay? So doing okay? Yeah, go ahead.
For the second one, in the denominator, do the signs of the velocities.
So, this is all done at speeds. Yeah, sorry, this is all done with speeds. So, in other words, with V1 and V2 positive. Okay? So I take everything positive, I know the result is going to be this or this, I can figure out the direction myself. And the nice thing is that relativity at least does not screw up this part. If you think the speed should be faster, it is faster. If you think the thing should reverse direction, it does reverse direction. Like all those basic things for velocity all stay the same, which is nice. So you can use there's one place where you get to use some of your classical intuition and it still works. Pretty much the only place. But you know, so like I said, I like this way because I find it faster and I can intuit this part easily, but if you find that confusing and you'd rather just set up the coordinate frames, do that, right? This is not a race. Okay. Good then. Let me just comment on one little thing that I won't give you the whole answer to because it's not on the test. Teachers hate that phrase. But just suppose for an instant, this train is traveling at 0.7 c, and I'm standing here, and I throw the ball straight up at 0.8 c. Of course. So, in your reference frame, you see going at an angle. Right? So what's my hypothesis?
That requires math.
If you could already tell me the problem, the hypothesis is greater than 1. Oh. That's because this is wrong. Yes, 0.7 squared plus 0.8 squared is greater than 1. The square root is still greater than 1. Yes, that's bad. That's because this is wrong. Transverse velocity, meaning velocity that's not moving in the direction of motion, also has to change. Why does it have to change? The y coordinate doesn't change, but the time still changes. Time affects everything. Therefore, there's still a change. You can work that all out. In fact, you do the same thing with the y instead of an x. And you can work it all out yourself. It's kind of fun. But we're not going to use it. I used to teach it. I wrote the most fiendishly difficult problems about it. But anyway, I grew that out in favor of covering other things. So you don't need to worry about that. I'm just letting you know. Kind of fun. Closely related to that question, that challenge question from early on about the laser above Jimbo's head. Right? The y components of your velocities also get transformed. That's what it is. Okay, but you don't need to worry about that. Just a little teaser. You're always welcome to look into that more on your own. Okay, we need to practice. Need to practice? Okay, good. Let's practice. We can do this fast, right? Sure. We can do this fast. This part is not physics. Sure. This part's not a race. Well, this part's not a race. This part is
A competition.
competition, exactly. It's not a race. All right. You can use the same groups as before. I don't care. I don't remember what they were. You can change them if you want. But I want shifts up here. I want positions in integers between 1 and 10. Positive or negative is fine. I'll put the origin in the middle. Okay, so between negative 10 and positive 10 in integers, and I want velocity, the direction that is that is 1/10 of c. 0.1 c, 0.2 c, 0.3 c, 0.4 c.
Make it the exact same as someone else's.
I think we have 6 people. I think we should have a position of 6 and a velocity of 6.
Alright, what's our position?
Put a name so we can identify.
Our position is 6 and our velocity is... Alright, what's the name of our ship? Wait, but hold it. There's only 2 6s. Look at the number of people.
Let's call it the Feynman.
Well, there's 6 people in our group.
USS Feynman.
No, okay, I'll tell you. There's 6 people in our group, so it's the name of the ship's gonna be Satan. It's gonna have a position of 6 and a velocity of 6.
What if you offend someone?
I hope I do.
Sucks to be them. They can get over it.
No, but we have a teacher in our presence. We'll get in trouble.
Alright, fine. Anyone have a better idea?
No, I think that's a pretty good idea. Just go for it.
But it's so uncreative and overdone. Such an overused joke. I like that.
It fits all the parameters. Just go.
Actually slow.
The yellow submarine again?
Alright, yeah, someone else could do it, but I'm not writing it. I can write it.
So, who wants to say that? No. Think about that.
Just go write it.
Dude, if I go write it.
No.
Hey, he's writing it, so we can just blame it on him if someone doesn't like it.
Oh my god!
It's too late. It's too late. He's going. There's no turning back now.
There's always turning back.
No, there's no turning back now. Oh my god, he's actually doing it. Wow.
You wrote it? It's been written. It's been written?
Oh, no, it's gone. It's gone. We're okay.
No! Watch him write Saturn instead.
Saturn?
No, satin like silk. Satin and silk.
Yeah, of course you will. You said okay, good. We're ready. You know what? I will let you choose your own target. That will avoid you trying to shoot someone who you can't hit. Because there are a few of those, right? So most of you guys would move. We got a decent distribution. Okay, good. Actually, everyone can never hit everyone here. It looks like. All right, great. So that's good to know. Okay, so oh wait, no, you still can. All right, so here's how it works. You have a torpedo. And now we really have to think about what this means. The muzzle velocity of your torpedo is 0.9 c. Now that's 0.9 c relative to what? The thing that fired it, meaning your ship. Okay? And the question is, what time to set on the clock? So the torpedo has a clock on it. That's its timer, right? It's going to blow up when the timer goes off. So the timer starts right when you fire it. So what time do you set on the clock to so that it will explode right when it hits the other ship? Okay. This is not an easy problem. This is a level 2.5 problem. So it's a good thing to practice on. Why don't we take the rest of the time, so please don't pack up. I will tell you when we're done. But take the rest of the time to at least talk about why this is a tricky problem. Okay? I'll let you guys talk with yourselves about at least an approach, like how are we going to figure this out. It is not an easy problem. If you think it's easy, you are definitely not thinking hard enough. A lot of reference frames here, right? Which ones do you care about? What? You may pick anyone to fire at, whoever you want.
Can we fire? Yeah, let's fire at ourselves.
Alright, go ahead, pick a boat and then talk about how can we do it.
Okay. Here's what I
We're shooting ourselves.
Do you guys want to fire at Bob?
We're the other end, and we don't like to be given.
Let's be out fire at Bob.
Anyway, we're not supposed to calculate it right now.
No, we're supposed to think of how to calculate it. I'm just writing down values.
Oh, sorry. Position and light seconds. Position and light seconds. Makes everything easier.
Okay.
Yeah, position and light seconds. That'll make everything faster. So they're doing relativity right now. And so they're trying to do they put their ships up there.
I'll tell you people that want to.
Alright, wait, let's think about it. Light seconds. What's the notation for light seconds?
CS.
CS, yeah. Alright, velocity.
Or Satan.
That's right. Alright, so the reason this is so tricky is because, yeah, we have our timer, but time gets all wacky moving between the reference frames. So it's going to be hard to figure out what time we should actually set it to.
Time proper for the torpedo.
Which, you want to try and figure that out? You know, the other reference? Yeah.
And then we also have to consider the ship would, the other ship would moving.
Yeah, but you also have to consider
Not care about any reference besides Bob and
We have this torpedo.
but we care about the torpedoes reference frame too.
only those three.
And
Everybody else doesn't matter.
and the reference frame from Williams Bay and none of those.
No, we don't have to worry about that.
We have to worry about Bob.
Screw them.
No, the origin doesn't actually matter. None of the other ships matter. We just have to.
We're the origin, guys.
Yeah,
We're the origin.
Well, we can set the origin, and then,
Yeah, we're making the origin us. And that means the distance is 15 light seconds.
Yeah, basically we just have to we have to set up the vectors for each of them at when the
There's two events. There's when the torpedo goes off, and then there's also
there's two. Well, here's the thing. Yeah, there's two events. There's when we fire the torpedo and when the torpedo hits the other ship. And we need to find the vectors of those, and that's going to be the hard part because we're all moving at relativistic speeds.
So we need to figure out first the distance the other ship will travel before we can find out the time, right?
Yes.
So no, we need to basically trying to find the time it takes for the torpedo to travel. But the ship, Bob, is traveling towards the torpedo, so then we have to track that time.
Hold on a second. This is actually a lot easier for us. Listen, our torpedo is moving towards them at 0.9 C. They're moving towards our torpedo. Yeah, I know. Their torpedo is moving towards us. I mean, they're moving towards us at 0.9 C.
I don't think we're towards the origin at point 9.
Please, real fast. I'm sorry, I wish we had more time to work on this. There are other things I also want time to work on. So let me tell you, I have homework.